Good afternoon once again. I still remain with Dogwan from Kampala Islamic Secondary School. Our discussion today will be basically on numerical. Yesterday was mechanic. So sorry for not finishing the last item yesterday, but we promised that whenever we are going to start that mechanics, we are going to continue from where we stopped. That was on the number of vacation. Today, look at least some numbers on numerical, and our main discussion is going to be from item 1 that was set by and first by, meaning that we are going to discuss two items. On our first item, that was the UNNASE mock. We are saying a construction company has been awarded a contract to install a drainage channel alongside a newly constructed road. For planning purpose, the engineer represents the drainage channel by the curve. The curve is given there, y equals x cubed minus 7x plus 6, while the road is represented by the x-axis, that is at the line y is equals to 0, to determine the points where the drainage channel intersects the road. The engineers intend to sketch the graph of the curve and estimate the series points of intersection within the interval of -4 up to +3. So they are saying, in addition, the company plans to construct a public washroom in the region enclosed by the drainage channel and the road between x equals 2 and x equals 3 to access whether the available land is sufficient. The engineer will estimate the enclosed area with 6 ordinates if the estimated area is less than 4 square units. The site will be considered too small for the purpose for the proposed washroom. The company also intends to purchase a cylindrical concrete culvert for the drainage system. The quoted dimension of each culvert, a radius of 8.45 centimeters and a height of 120.2 centimeters, corrected to the nearest decimal place. Before placing the order, the engineer wished to verify the reliability of these measurements. They will determine the percentage error in the volume of the culvert and proceed with the purchase only if the percentage error is less than 1.0%. So they are telling us here that we should help the construction company to take the informed decision using the above statement. So when you look at in our item, you realize that the first paragraph, let me hope they have shared it with you there. The first paragraph, it is the specifically dealing with the allocation of routes, whereby we have to locate the routes and we see the city points that will cross the x-axis, that is at the line y equals 0. And in the second part, you see that the question there may be talking about the tropezium rule, where the tropezium rule this time they want us to find the approximate value, but the approximated value should be less than the 4 square units. And in the last part, they are talking about the error. In the error, you look at the part where you can see that where they are talking about to verify the reliability of the measurement. That part there only makes the question somehow tricky, because whenever we want to verify reliability, meaning that we should be talking about the relative error. And you know, when it comes to relative error, how we always do it, we always get the estimation, we divide by 2. That's the half of what the question is having. So let us have our discussion to start from the first paragraph. That is the paragraph 1, where we say that the question is talking about the location of routes. The paragraph 1, we look at the given expression given as x cubed minus 7x plus 6. So we'll have -4 less equals x less or equals to 3. When we talk about the location of routes, we always deal and the graph here. We can draw a graph in 2 different ways. We have the graph called a one-way graph, where we can use the expression as it is given, or we can also draw this graph into a two-way graph. A two-way graph means splitting the expression given to us into two two given parts. So that is what we are supposed to base on. At this time, I will use all the two methods. I will start with a one-way graph. For one-way graph, we have to use the given values of x to get the value of y, meaning that I will have to tabulate my expression. My table, I'm going to start with the value of x, -4, -3, -2, -1, this is 0, 1, 2, and then they have said here the last value is 3. That is our derivation. Meaning, we are going to be getting the value of y by putting in where we are seeing x. Where I see x, I put the given value of x so that we can obtain y. Start with x equals to -4. So out, that is the -4 to power 3 minus this is 0 also. Then when our x is 3, that is for my x-axis. For my y-axis, I am going to use a scale of 10. That's for these are working. So this is 10, 20. When here we can go to -10, -20, and -30. Scale of 10 I've used here is representing a unit of 2 centimeters, which means if we are asked to get the scale, we can say 1 centimeter. I said x-axis 1 centimeter to be 1 unit. Then on the y-axis, 2 centimeter make 10 units. That is for that case. So I'm going to plot this. Our first point is -4, 30, -4, 30 is around down here. Then we also go to -3, 0. -3, 0 is at this point. Come to -2 and 12. -2 and 12. 12 is slightly above 10. It's a difference of 2 small boxes. So this can be around here. Then we look at -1 and 12 also. -1 and 12, they have the same value. Come to 0 and 6. 0 and 6, you realize that 0 and 6 is somewhere here. Then 1, 0, which is here. First we have 2, 0, which is here. We'll also have the 3, 12, which is above here. Meaning that on our graph, this arrow is going to move like that. So this value this, then this like this, then we have that. So this is equals to x cubed minus 7 x plus 6. In our scenario, it was saying that we should do that the issue was to determine the point where the drainage channel intersect the road. Remember, they have said that our road is the same as the x-axis. That's the line y equals to 0. So meaning that I'm going to represent this to be our road. That is at x-axis. Meaning that when you look at in our roads, we have 3 points that is intersecting this road. We are having a point at x equals negative 3. That's the point negative 3, 0. We are having another point at x equals 1. That's the 1, 0. And we are having another point at x equals 2. That is the 2, 0. Meaning, I will say the coordinates of the point where the drainage channel intersect the road are first one is negative 3, 0. The second one is 1, 0, and 2, and 2, 0. That is concerning our paragraph 1. In the paragraph 2, they are saying that in addition, the company plans to construct a public washroom on the region enclosed by the drainage channel and the road. So the region contained by this drainage channel and the road is what they are talking about. And they are saying the region is between x equals to 2 and x equals to 3, meaning that the toilet or the washroom should be constructed between this given region. So when you look at that, they are saying that it is the area, meaning that the area to be sufficient, we have to talk about the trapezium rule. That's when I look at the area. So we are going to look at the region between 2 and 3, and this area should not exceed 4 square units. For our second paragraph, we are going to say the area that is the energy given by getting out, say, of 8 half of that. So we get the values, the last and the first, difference between the last and the first value. Can also call them in a different way. Plus the 2 times the middle values. You can also call them in a different way. In the other way, we say that this can be given by half h. If you don't want to write it like that, which is by not plus the y1. So meaning that this is the same as 2 into 2 into y1. So we can say this. Another one plus the dash. Another one. All those ones are right. So we are going to look at given expression where they have said that the value is x equal to, so it will act as our limit given the expression for the rod, that is x plus 6, the x. They have said that here that is under 6 ordinates. Ordinates means that we have to get the our range that will be given by the big value minus that. So we are going to have the 3 minus 2 divided by the 6. We said under ordinate we subtract. So you'll have around 1 divided by 5, which is the 1 divided by 5, which is around 0.2. So this is 0. And around 0.2. So we are going to use the 0.2 to get the range. So if I have the values of x, that will give us the first lower limit of 2. The limit until we reach 3 using an interval of 0.2. So meaning we are going to have this is 2.2, 2.4, 2.6, 2.8, and now we reach 3. Then we'll have a part where we are supposed to use them now for the substitution. That is the 7 x plus 6. So after that, let's get the first value. That is for my x equals to 2. So when you have 2 to power 3 minus 7 of 2 plus 6, this value is 0. Depending on the number or the estimation, they have told us here that the values, we are not given the approximation, the numbers of decimal points. So I'm going to use any of my choice. I can use 2 decimal points. The next one is for 2, x equals 2.2. So if you have the 2.2, that is the power 3 minus 7 of 2.2 plus 6. Our answer here is the 1.25. Like I said, we are putting into 2 decimal point. Go to another one, that is 2.4. So for 2.4 to power 3 minus 7 into 2.4 plus 6. This is 3.0. 3.02. Go to another one when we are having x equal to 2.6. 2.6 power 3 minus 7 into 2.6. Have 1.25 plus 3.02. We have 5.34 plus 8.35. So this is giving us 17.96. So meaning that we can now get our area by putting in the formula. I'm going to say area is given by R of our h, that is the interval of 0.2, in the bracket the sum of the first, the last and the first value, that is the 0.0, plus the 2 times the middle values, that is 17.96. So we'll have 12 plus 2 into 17.96 times 0.1. So this is our area. Here is the 4.792 units. That's a square unit. So we can go back to our scenario. In the scenario, they are saying To access whether the available land is sufficient, the engineer will estimate the enclosed area with 6 coordinates. If the estimated area is less than 4 square units, which is better than already, the site will be considered too small for the proposed room. Meaning that in our conclusion, we can compare the area we have got with the given area. And if you look at the area we have got with the given area, you realize that the area we have got is bigger than the given area, which means it will not be less than the 4 square units. So the conclusion there could be the site will be considered big because this one here is not to be considered small because it's greater than 4 square units. So that was the concerning the paragraph 2. Then paragraph 3, it was about the paragraph of the error. And the error, they are talking about the error that should be got from the volume of a cylinder. And if you know how to get the volume of a cylinder, this question can be very easy. But like I said before, that the tricky part is where they are saying the engineer wish to verify the reliability of this measurement. We said whenever we talk about the reliability means the relative error that may be applicable, that is there in a given volume, meaning that we should get the relative error for each and every part, that is in terms of height and in terms of radius, basing on the formula for the volume of a cylinder. We will have to make the derivation of the percentage error in terms of R. So in our side paragraph, we'll have to get the volume of a cylinder, which is given by pi r squared h. So in that pi r squared h, you realize that basing on the differential approach, you realize that this volume will only depend on the radius and the height, because the pi is taken to be a constant value in this formula. Meaning that in my derivation also, I will only go and base on the radius and the height, but I will consider the pi as the constant volume because we have to get the percentage error. So I'm going to differentiate this using the product rule by maybe considering this one to be our U and this one here to be our V. That is for the differential. So if I differentiate the first part, this one is going to give us the small change or the error in V. So meaning that the error in V, if I pull out our constant, then I differentiate now the R and the H. If I try to keep the H constant, you realize that I will differentiate R. But this R we are going to differentiate should be having the small change because we have reduced it. Then with the H. Then also at the same time, I will differentiate H, keeping R constant. Meaning here we are going to have the R squared. If I differentiate the H, will remain as it will go to be a 1, which means we will have the R squared, the H. So meaning in by R of H plus by R squared what we have. So that is this is my first expression, and then this is my second expression. I'm going to say from equation 2, I'm going to divide this equation 2 by equation 1. We're looking at how we can come up with the percentage error in the volume of this cylinder. So I'm going to divide what is on the left hand side with what is on the left hand side, and what is on the right hand side with what is on the right hand side. Meaning that we are going to have the V. being given to B. This one means that it is given as the change in volume. So the change in volume, let us look at how the expression is going to be. Get the pi r squared h, and then we also divide by the exact value, that was the pi r squared h. So you have this one here. Remains. I am going to split the LCM, put this one over this, and even that one over that. So you realize that you're going to have 2 pi r, the r of h, divided by pi r squared h. Then plus, this is the pi r squared pi r squared h. So you have you can say first part will go and the r and the r. The r will go one, but the h will have to go. So up there you're going to have 2 change in r, because all of this one has gone. Then divide by the 1 r that has remained down. Then the next part will have this one as the expression for the error in the volume of a cylinder. Now we are going to look at the percentage error, because they are telling us here that it should be less than 1.0%. But we are given the exact value of the radius and we are given the exact value of the height. Like I said before, that the only thing we have to look at here, we have to look at the relative error. The question has not asked for the relative error, but there is a statement talking about what requires relative error. And for the case of a relative error, we said that to get the relative error, we get them from the estimation of the number. Like they have told you to get, maybe to round up your figure to 0.5. That is the one. That's the one. Decimal point. Let me say 0.1. That's the best thing on our estimation. So this 0.1 is got by dividing it by 2, meaning that if I get the 0.1 divided by 2, you end up getting 0.05. That is if I have a plus or a minus of 0.1. Here they're telling us that should be corrected to the nearest decimal place, meaning that the nearest decimal place will come from the numbers of DPs that is given here. Because we are not given the numbers of DPs, we are going to correct it to the nearest 1 decimal point. So I look at my radius as the 8.45, then I as the 0.2. This is centimeters. Even this is the centimeters. All these ones here, I'm going to take my relative to be 0.005, because we are taking our estimation to be given as 0.1. Meaning, if I want the error now, the error in each of these will be given by the relative, and then we divide by the exact value. I'm going to start from the error in the radius. The error in radius, I'm going to get at once as the percentage error. We may also be having another formula that will give us the same answer. So the percentage error in the radius, we are going to get the relative error, that is 0.05, divided by the exact value, that was 8.445, then I multiply by 100%. So this will give us 0.05 divided by 80.45 times 100. Here we are getting 0.06 to 2%. Then I also come and get the percentage in the percentage error in the I. That will also give me the same relative error, 0.5 divided by 1, 20.2 times 100%. So you'll also have 0.05 divided by 120.5, 120.2 I mean, times 100. So this is a 0.04, can say 16%. So what we are obtaining here, is representing the change in R divided by R. This is representing the change in H divided by H. Meaning that the percentage error, I've got the value of the R over R and the H over H. So I'm going to say the percentage error in the volume. I'm going to substitute for those values in this statement. For this case, they are saying it is 2 times the R over R, which is 0.0622%. The H over H, which is 0.0416 of that value times 0.0622 plus 0.0416. So when you look at here, the value obtaining is 1.66%. So when you look at this 1.66%, this 1.66% is acting as the percentage error in the approximation of the volume of that given cylinder. And when you look at its value, you realize that it is less than the 1%, 1.0% they were talking about. Meaning, in our conclusion here, we will have the conclusion based on the statement. The statement we are saying that they will determine the percentage error in the volume, the culvert, and proceed with the purchase if the percentage error is less than 1.0. So we can conclude by saying they will proceed with the purchase of a cylindrical concrete culvert for the drainage system since the percentage error in its volume is less than 1%. So that was the item 1 under the mock called UNNASE. The conclusion, I repeat, we say we will proceed with the purchase of the cylindrical concrete culvert for the drainage system. They will proceed with the purchase of a cylindrical concrete culvert for the drainage system since the percentage error is less than 1.0%. Error is less than 1.0%. So that was it. That our next item is going to come from Wakisha. That was still item 1. Wakisha item 1 will be our next item, still under numerical analysis. See you, first go and pray.